So normally we're going to want to use StatCrunch or the calculator to conduct an ANOVA test if we can. But when we have summary information instead of data, then we can't use the calculator or StatCrunch to conduct the ANOVA test. So caution, the TI-83, 84 plus graphing calculators and StatCrunch can only conduct ANOVA tests when we have raw data. If we only have summary statistics for each treatment level, then we will have to conduct the test by hand. So again, we have to have actual raw data values in order to be able to use StatCrunch or the calculator to do that. They don't have programs built in to be able to do the ANOVA if we have summary information. So for example, determine the F-test statistic based on the following summary statistics, and then hint X bar is equal to the sum of N sub I times X bar sub I over the sum of N sub I. So in this particular case, we are comparing 4 different populations. So the null hypothesis would be that the mean from population 1 equals the mean from population 2 equals the mean from population 3 equals the mean from population 4. And the alternative hypothesis would be that at least one mean is different. Now, in this particular case, it doesn't say to conduct the entire hypothesis test. It doesn't say to do the entire ANOVA test. Instead, we're just supposed to calculate the F-test statistic. So what we're given here is that a sample of size 15 is taken from population 1, and likewise another sample of size 15 is taken from population 2, and from population 3, and from population 4. So all of the sample sizes are the same. And the X bar for the first sample is 105, X bar for the second sample is 110, X bar for the third sample is 108, and X bar for the last sample is 90. And then we have the sample variances here. Now note that these are the variances, not the standard deviations. So this is S1 squared is 34, S2 squared is 40, S3 squared is 30, and S4 squared is 38. So again, these are the 4 sample variances from the samples that we've taken from the population. And again, we want to calculate the F statistic. Well, just want to remind you how we go about calculating the F statistic. In order to calculate the F statistic, we have to calculate the sum of the squares due to error, and then the degrees of freedom due to error, and then we use that to find the mean squares due to error. We also have to find the sum of the squares due to treatment and the degrees of freedom due to treatment, and then we use that to find the mean square due to treatment. So that's what we have to do here, and we can do that with the information that's provided. So first of all, remember how we find the SSE, the sum of the squares due to error. We take each sample size minus 1, in other words, the degrees of freedom, times the variance, and we add those all up. So I'm going to do that first here. So I'm going to find the SSE. And so for the first sample, I'm going to take the sample size 15 minus 1, so that's really 14 degrees of freedom, and I'm going to multiply that by the variance of the first sample, and the variance is 34. Now again, I just want to caution you that this is the variance, so this actually is S squared right here, so I don't have to square it. Now, if they tell us the standard deviation here instead of the variance, then we will have to square it because we need the variance right here. For the second sample, also going to be 15 minus 1, or 14, times the variance, 40. Third sample, 15 minus 1, or 14, the degrees of freedom, times the variance, 30. And for the last sample, 15 minus 1, or 14, the again, the degrees of freedom, times the variance, 38. So if I bring in my calculator here, now I'm going to, instead of typing 15 minus 1, I'm going to just say that's 14 times 34 plus 14 times 40 plus 14 times 30 plus 14 times 38. So that is 1,988. That is the sum of the squares due to error. Now, I also need to find the degrees of freedom due to error. And if you will remember, that will just be what we get if we add up all of the degrees of freedom for all of the samples. So in other words, that's going to equal n minus k, where n is the total number of data values and k is the number of categories that we have. So the degrees of freedom due to error. Now altogether, we have 60 data values. We have 15, 15, 15, 15. So there are 60 data values altogether. So that's what n is. Minus, there are 4 different categories. So that's what k is. So 60 minus 4, which is 56 degrees of freedom due to error. So I know the sum of the squares due to error. I know the degrees of freedom due to error. So I can find the mean squares due to error. And that is going to equal the 1988 divided by 56. 1988 divided by 56 is 35.5. So the mean square due to error is 35.5 for this problem. So now that we have that, we need to also find the mean squares due to treatment. And in order to do that, we have to first of all find the sum of the squares due to treatment. Now remember how we do that. For this, we're going to take each individual mean minus the overall mean and square it, and we're going to multiply that by the sample size. So in this particular case, we don't know what the overall mean is. So we're going to have to figure that out, and that's where this hint comes in. So if I take each of the sample means that are given and multiply by the sample size and add that up and divide that by the total number of data values, that will give me the overall mean. So I'm going to find the overall X bar by taking each sample size. So like, for example, for sample 1, the sample size is 15 times the sample mean, 105. And then I'm going to do the same thing for the second sample. The sample size is 15 times the mean is 110. And for the third sample, 15 times the sample mean, 108. And for the last sample, 15 times the sample mean, 90. So again, I'm taking each sample size times the sample mean for that group, and I'm going to add those up. And then I'm going to divide that by the total sample size. So in other words, I'm going to add up the 15 plus 15 plus 15 plus 15. So I'm going to add up all of the sample sizes. Now, if I do that, 15 times 105 plus 15 times 110 plus 15 times 108 plus 15 times 90, that adds up to 6,195. And 15 plus 15 plus 15 plus 15 will be 60. So I have 6,195 divided by 60. So if I do that division, that's 103.25. Now again, that is the overall mean of all 60 data values. And so again, what I'm really doing is I'm weighting each of the individual means by the sample size and finding a weighted average of that. Now, I do want to point out a little shortcut that you can use. If all of the sample sizes are the same size, like in this case, we don't really have to do a weighted mean. If all of the sample sizes are the same size, we could just take 105 plus 110 plus 108 plus 90. That's 413. And if we divide that by 4, we get 103.25, the same mean. So if all of the sample sizes are the same, we don't really have to do a weighted average. We could just average the 4 means in this particular case. However, if all of the sample sizes are not the same, then you can't do that. If all of the sample sizes, if any one of them's different, then we can't do that by just adding them up and dividing by 4. We have to do a weighted mean like this. Now that I have that, again, I'm going to take each sample size times the individual mean minus the overall mean squared. I'm going to do that for each sample and add it up. That's going to give me the sum of the squares due to treatment. So the SST is going to equal. Now for my first sample, the size is 15, so I'm going to have 15 times the individual mean is 105 minus the overall mean, 103.25 squared. Now I'm going to do the same thing for the second sample. So the sample size is 15 times the individual mean is 110 minus the overall mean, 103.25 squared. Plus for the third sample, the size is 15. The individual means 108 minus the overall mean, 103.25 squared. And last but not least, the sample size is 15. The individual mean is 90 minus the overall mean, 103.25 squared. So if I punch that in my calculator, I'm going to have 15 times parenthesis 105 minus 103.25 close parenthesis squared plus 15 times parenthesis 110 minus 103.25 close parenthesis squared plus 15 times parenthesis 108 minus 103.25 squared plus, last but not least, 15 times parenthesis 90 minus 103.25 close parenthesis squared. And so that total is 3,701.25. 3,701.25 is that total. Now, I need to find the degrees of freedom due to treatment. And again, just to remind you, that is here on the previous page, that is equal to the number of categories minus 1. So in this particular case, we have 4 categories, 4 populations. 4 minus 1 is 3. So we have 3 degrees of freedom due to treatment. And so our mean square due to treatment, I'm going to write that over here, our MST is going to equal the sum of the squares due to treatment, 3,701.25, divided by the degrees of freedom due to treatment, which is 3. So if I take the 3,701.25 divided by 3, that is 1,233.75. So now I have the mean squared due to error up here, 35.5, and I have the mean squared due to treatment right here, 1,233.75. And the F statistic is the MST divided by the MSE. So F naught is going to equal our MST, which is 1,233.75, divided by our MSE, which is 35.5. So 1,233.75 divided by 35.5, that is equal to 34.754 if I round to 3 places. So this is 34.754 approximately. So that is our F statistic. Now, again, the point of this example is if we have summary information, which is what we have here, we were given the summary statistics, we were given the sample means and the sample variances and the sample sizes, we were not given the individual data values. So when we have this summary information, we have to do the problem by hand. We can't do the problem with the calculator or with StatCrunch. So we have the F statistic. Now, that's all we had to do in this example, but we then could continue the ANOVA test if we wanted to. We would have to choose a level of significance. We would have to either use the p-value approach or the classical approach to conclude our test. For example, if we were going to use the p-value approach, the p-value would be the area to the right of this. If we have 3 degrees of freedom in the numerator and 56 degrees of freedom in the denominator. So if I were to go to distribution and to the FCDF command on my calculator, in this particular case, my lower bound would be the 34.754. The upper bound would be a big positive number. Again, I have 3 degrees of freedom in the numerator and 56 degrees of freedom in the denominator. And so that would give us a p-value of 8.06 times 10 to the negative 13th power. So if I were to round that to 4 places, that would be 0.0000. It's like really, really small p-value. So we would reject the null hypothesis that all 4 means are equal because that's such a small p-value. We would reject this, and we would conclude that at least one of the means is different from the others. Now, again, you weren't required to do that in this particular problem. That's just what we would normally do if we wanted to complete the entire ANOVA test.